So this is going to be page 129 in your composition book. This is congruency number 3, the third lesson in the congruency unit. This one's going to cover yet another postulate for determining congruency of triangles. First things first, what does congruence mean to you when we're talking about two triangles? If two triangles are congruent, what are they to each other? What's their relationship? Equal. Okay? Everybody say congruent. Right? Now, why don't we just use equal? Diego, if equal works, if you can say two triangles are equal, why don't we just say the two triangles are equal? Why do we have this new word congruent? Why? Why do you have a new word? Because this is new for most of you, right? How many have heard congruent before this class or before this, right? You've heard it a little bit. Good. That's nice. I appreciate that. But for general purposes, congruent meaning in geometry might be new for a lot of you, right? Why do you need a new word? Why don't you just say equal? We've got equal. Why not just say these two triangles are equal, right? Why do you use congruence? What?
Because one is rotated and technically both is equal, I guess.
Okay, not bad. I like where you're headed with this. Who else? Why use a new word? What do you say, Kate?
Maybe because equal is like equation.
Okay, because equals for other things, right? And equal, so I'm going to present it to you like this. And I like where you're heading. What I think we're trying to say, we, all of us together, in the different ways we're saying it, I think what we're saying is this is more complicated than just equals. There's additional factors here that make equal okay. I get what you're saying, but congruence has this sort of additional idea to it. And here's the idea the way I see it, right? If you're asking, are these two triangles congruent to each other or exactly the same, you're trying to look at 1, 2, 3 different angles on this one and see if they match up with 3 angles on this one, and 1, 2, 3 sides on this one, and see if they match up exactly with 3 sides on this one. It's not just one aspect of equality, right? So I like equals for the way we've used it before. We say the number 5 equals the number 5, right? 5 equals 5. I could write 5 equals 5. Boom, done. It's a singular aspect of equality. Now you're talking about 3 angles on each, and 3 sides on each. There's at least 6 aspects of equality that we're kind of considering through all this. Are you with me? So congruence to me is sort of a bigger word. It says we looked at all 6 aspects and they're all exactly equal between the two and they line up in the right spots. It's more than just equal. There's additional ideas we're looking at. And that's why I try to explain the congruence symbol to you. It's not just an equal sign, but it's got a squiggly above it. Kind of like an asterisk of this is not only equal, this is congruent. Is this okay with you? So hence the new word congruency, right? So now you're asking, so here's the setup for this one. Given 2 triangles with equal corresponding angles and with given 2 triangles with, and I would like to say 2 in here, sorry if I forgot to write that, with 2 equal corresponding angles and an attached equal corresponding side, what can we say about the 2 triangles? And what are we going to say? This is our 3rd lesson, so we're going to bounce forward a little bit. We're going to say they're congruent. Why? Because there's yet another postulate, the angle-angle-side congruency postulate. And the proof for this is in the Schoolgy work that you're doing. You're going to roll through that and see the proof in the background of this and why this works, right? This is the presentation and the setup for it. So what is this postulate? By the way, what is the difference between a postulate and a theorem? And this is kind of complicated because, again, some new words. What's the difference between a postulate and a theorem? So here it is. A postulate is a definition. So this is a definition. A theorem is something proven with postulates. Okay, so here's a definition. The number of degrees in a circle is how many? 360. We define that. We made that up and defined it. Now it's a definition. Now we all use it. So if you say to me, rotate 360 degrees, right, and I'm standing here, I can go like this, and you know because we define that. That would be a postulate. It's a definition. But now if you start to use 360 degrees or some aspect of the degrees of a circle in a proof, you're going to say, well, something rotated 90 degrees, and that set up something else. And now we have this we can say. That becomes a theorem because it's using definitions in its proof. Is this okay? Okay, because in the school G's, they're going to ask you over and over, what's the difference between a postulate and a theorem? And when I was a student, my brain was always kind of reeling. I'm like, the word postulate I had never heard before, and the word theorem, I had heard theory, but I hadn't heard theorem, which is specific to geometry. Okay, so it's a postulate, it's a definition, two triangles with equal, and it should say again here with two equal, and I'll show you that right now with a diagram, with two equal corresponding angles and an equal attached corresponding side are congruent. So, are these two congruent? Everybody look up here at these. Look at these two triangles. Do they look exactly equal to you?
Nope.
No? Why? Doesn't this one look a lot bigger?
Yes.
And this one look a lot smaller? So what have I purposely done with this? This is not, what do you say about these two? Not drawn, do you remember it? Good, thank you, and I can't write it. I appreciate you saying it. Not D-R-A-W-N, drawn to scale. I have purposely drawn one bigger and one smaller because I don't want you to look at the size and go, oh, they're both equal. That's not the way it works anymore. Now you have to look at the data. You have to look at angle A, matches up with angle D. These are the same measurement. This one's got one tick mark, this one's got one tick mark. They're both an equal measure number of angles. This B has two, so preceding, two tick marks precedes to this one. So this angle and this angle correspond in location to this angle to this angle, and this one's equal to this one, this is equal to this one. So I have two corresponding location angles of the same measure in two different triangles. Now I move to the side beyond that. It goes AB, and then we look at this side beyond it, one tick mark, and the side beyond these two, one tick mark. We have a setup here of an angle side of this one in corresponding locations match up with an angle side of this one, and that fits the angle side congruency postulate, so they are congruent even though they look completely different sizes, right? And the easiest thing for you to think about of this not drawn to scale, what if one of these was closer to you here and the other triangle was pulled back? Wouldn't this one closer to you be bigger? And this one back here smaller. But if you moved them right here, they're exactly the same size. Does this make sense? So that's the whole idea of not drawn to scale. We're trying to get rid of the idea that you're matching. You're just looking at them and going, oh, they look the same size they are. That's not what you want to do anymore. You want to use one of the postulates at your disposal. And now you have three. This is the third one. You have side, congruency postulate. You have, I believe, side, angle, side was the prior congruency postulate. And now you have angle, side. All right, so not drawn to scale. And then notice that we get to say triangle ABC, this one, is congruent to, that's poorly written, but that's an equals sign with a squiggly over it, or a little, I forget what they call it, okay, equal to the triangle DEF, right? That's the way we're gonna write it in terms of symbols. So turn to one more. Are these two congruent? Why? Notice we're matching 23 degrees with 23 degrees. Those two angles are the same. 47 degrees with 47 degrees, and the side next to it is 10 and 10. This goes in an angle, side pattern. This matches it, angle, side. These two are congruent because of the AAS congruency postulate. Okay, some things to just highlight. Number one, corresponding. Corresponding means matching locations. So corresponding angles are angles that if you put these over top of each other, they line up in the same place, the same position. So in other words, A lines up with D, therefore B, if I rotated this, I could slide these on top of each other. A would be on top of D, B would be on top of E, and this side would be on top of this side, right? Those would be matching locations, or corresponding is the word you're using for that. Number two, I forget how many, look up here and see this symbol? See these three dots? Do you know that this symbol means therefore? This is a shorthand way of saying therefore. These things are match up because of the angle, side congruency postulate. Therefore, triangle ABC is congruent to triangle DEF. I think it asks you this inside of school G2. What does this three dot symbol mean? In math, it actually has a meaning. It means therefore. Okay, 3 dots in a triangle like that. I am aware that there's 3 dots in different symbols, but for math it means therefore. Okay, so your other meanings may be true too. In this case, it means therefore. So this would be the angle side congruence postulate. There's going to be 2 more after this, and you're going to wrap up all of the congruency postulates, and then you're going to move into a unit on similarity, which will be not equal, 2 shapes equal, but proportional. Right? Okay, so stop that.